right, we are now recording. And if you have a microphone, please hit mute so we don't hear a background noise. So we're going to talk about the first 5 units in part 1 and introductory to physical geography. So here we have a picture of the Earth, and the Earth is 7,918 miles in diameter roughly, and it has a circumference of about 24,900 miles. It is slightly wider at the equator than it is at the poles, and that's because of the centrifugal force of the Earth spinning makes it slightly wider at the base than it is at the poles from the spinning, essentially. And the first unit is Introductory to Physical Geography. And this is a picture of Lake Superior along the Pictured Rocks National Lakeshore. And there's an interesting video of this, some of these rocks collapsing. We'll take a quick look at that. If this works. Trying to get the sound on. The video goes on for about another minute. It's basically someone telling his friend Brad to back up. But then you can see that's erosion in action. These rocks are made from limestone. Limestone is fairly hard, but not incredibly hard. So wear and tear and freeze-thaw cycle can break down the rocks, and they do collapse like you've seen in that video from time to time. This is a picture of Phoenix, Arizona. I have a sister-in-law that lives there, and it's a booming city because it has lots of cheap land and warm climates that some people find appealing. It's on the top of a reservoir, so they have a relatively reliable supply of water, but it's been growing very quickly, and because of that, they've had to be a lot more careful and judicious with their water, and they've had to use less of it and spend the water, so to speak, more carefully. People like moving away from cold, snowy weather, and after the ice storm we had, you can hardly blame them. But my sister-in-law says it routinely gets up to 110 degrees during the summer, and it's only getting worse as more of the city is built up and turned into pavement and parking lots, and more buildings are added, and there's less shade. It's creating something called a heat island effect, which means large urban areas are hotter than their surrounding rural areas because of buildings and concrete and metal and so on. And that actually increases the temperature of cities compared to their countryside around them. One way to counter the heat island effect is with shade. Planting trees is a good way of making cities more livable. It looks a lot nicer. It significantly cools the areas that are shaded. Sunlight doesn't hit the pavement as much, so it doesn't suck up the heat and then release it at night. But it actually costs a lot of money to have trees. It takes land and money and water to build and plant and maintain them. And often wealthier neighborhoods have more shade, and poorer neighborhoods often have a lot less shade. So if you have an area where there are a lot of poor homes or rentals where the landlords don't necessarily care that much about having a nice place for people to live, you will very often have fewer trees, more pavement, and it can be significantly hotter in poor areas with less shade and fewer trees than in urban areas that are a little wealthier. This picture here shows the Phoenix area, and the areas in red are areas that are hotter than the areas in blue. This picture was taken in, I believe, July, and there are certain areas in the metro area that are 115 to 120 degrees. And then there are areas that are about 15 degrees cooler in Scottsdale and some of the more affluent suburbs that are more likely to have grass and trees and so on, and less likely to have just giant slabs of concrete. So shade can significantly reduce the temperature of a city, although it does take some money in order to plant and maintain trees to create shade. So the book talks about the subfields of physical geography, and the main subfields of physical geography are geology, meteorology, botany, ecology, zoology. Those three make up biogeography, living geography. Pedology, soils, it's pretty boring, but we'll have to talk about it a little bit later. Marine science and hydrology. So again, zoology, ecology, and botany are interesting because those are biogeography, and they deal with living plants, living animals, and the interaction between the plants and the animals. So 5, 4, and 3 are especially interesting when it comes to the different subgenres of physical geography. So something that's, I'll have to excuse my voice, it's a little rough. I'm just getting over a cold. One thing that's mentioned in the book that's very important in any science is the scientific method, and this is a way of knowing or learning about the world. It involves having a hypothesis, which is a tentative explanation of observations or measurements that help them make a general prediction. An experiment, that's a test or trial or procedure that's used to try to learn something. A theory is something that is supported by an experiment. And then a scientific law are principles that are believed to have no exceptions. There aren't many scientific laws. One might be the laws of gravity. This is something that Isaac Newton came up with in the 1600s. He was the famous Scottish physicist. He invented algebra, and he's considered by many to be one of the greatest scientists ever. And he developed laws of gravity that people have not been able to disprove or discredit in any way. So there's a law of gravity developed by Isaac Newton, some other laws, but scientific laws are relatively rare because it's easy to prove or disprove something with some exceptions. But if there are thought to be no exceptions, that's considered a scientific law. So the Earth has different Earth systems of science. An open system is a system where energy and mass and momentum can move freely between the border of a certain system. A lake would be an example of that. A lake is not a completely isolated, enclosed ecosystem. There's rain that comes down, rain and water that evaporates, and so on. A closed system is self-contained, and there is no exchange of energy or mass across boundaries. An example might be an aquarium or a terrarium. Closed systems are a little unusual, perhaps a cave of some kind. But generally, most systems are open systems. And then we'll also talk a little about positive and negative feedback loops. So this is an example of a reservoir, which is an example of an open system. And in this diagram, you can see sunlight comes and hits the reservoir, and that warms the water, and that can cause evaporation, which causes moisture to rise into the air. As that moisture rises higher up in the air, it gets cooler. It gets to a certain point where the coolness of the moisture comes down as rain or snow, and then that can flow back into the reservoir. Water from the reservoir can also percolate into the groundwater. So this is an example of energy, sunlight, and water moving within a reservoir, and it's an example of an open system. So we talked a little about positive and negative feedbacks. A positive feedback loop is basically when you have something that feeds upon itself and something happens and then that causes whatever it is to increase. So for instance, less sunlight hitting Siberia in the winter will often cause more snow. More snow will cover the ground with snow and white, which is lighter than soil. That will cause more sunlight to reflect, which leads to even lower temperatures. A negative feedback loop is something where something counteracts something else. So less sunlight hitting Siberia leads to lower temperatures, but that leads to greater temperature difference across Siberia and nearby oceans, and that attracts heat and moisture from nearby oceans to the colder temperatures of Siberia, which then increases the temperature of Siberia. So a negative feedback loop is cold weather leads to snow, snow leads to less sunlight hitting the ground, which leads to colder temperatures and more snow. And a negative feedback loop is colder temperatures lead to warm, moist air from the ocean coming into the colder area and warming it up. So those are examples of positive and negative feedback loops. This is Siberia. This is a very large boreal forest, mostly in northern Russia. And this is made up of coniferous trees or pine trees. And this is very similar to northern Canada and maybe the upper part of Michigan, the Upper Peninsula, a lot of coniferous trees. Siberia is relatively dry. There isn't as much rain, moisture, and snow as there would be in northern Canada, but it's an example of a large boreal forest, which are common above about 45 to 50 degrees latitude before you get to the tundra a little further north. There's an interesting experiment going on in northern Minnesota where scientists are trying to predict what the climate is going to be like in the near future. So they're isolating small pockets of the boreal forest in northern Minnesota, and they're increasing the temperature within these little cells to certain degrees to see how the plants within those little areas are going to react to them. So they have about a dozen of these small little cells, and they heat the inside of it, and some of them are 3 degrees warmer, some are 5, some are 10, and then they measure what is happening to the plants and animals and so on inside. And unsurprisingly, There are certain points where the plants can adapt, but then there are certain points where if it gets too hot, the plants and the lichen and grass can die off. So there really is kind of a breaking point where they can tolerate some change, maybe if it's slow, but if the earth heats too fast, it can be very devastating to lots of plants and animals and so on. I have a link to this on our website if you want to learn more about this experiment going on in northern Minnesota. So, dynamic equilibrium is when you have something that's going on where well, this is an example in South Florida. There's a certain amount of sand that's being deposited along southern Florida, and there's a certain amount of sand that's being eroded. But if the amount of sand deposited and the amount of sand eroded is roughly equal, then you have what's called something in dynamic equilibrium. Sand is an example. A lake could be another example. You might have a lake where some water is drained through rivers, but rain comes in and replenishes it, so the lake stays relatively stable. So that's another example of dynamic equilibrium related to water. This example talks about sand. A model is mentioned in your book. A model is basically a simplified representation of something containing a process or feature that is of interest. Physical geography today often use mathematical models to try to predict what weather is going to be like. Excuse me. What, one second. Sorry about that. What weather is going to be like. Models are often used to try to predict the paths of hurricanes. So a simple version of a model would be a globe or a map, but also there are many elaborate computer models that use algorithms to try to predict weather, especially in the near future or in the long term. So a climate model is done with computers that predict the weather um, and try to predict what global warming might be like in the near future. So models are used, some of them are simple, some of them are complicated to try to often predict future events. The book also talks about orders of magnitude. When you deal with geography, you deal with things that are very small, like tiny pieces of soil or chemical reactions at a molecular level. And you deal with things on a larger scale, covering the Earth and then possibly even the solar system or beyond. What we generally focus on is this orders of magnitude uses the meter as its starting point, and most of what physical geographers concern themselves with is something larger than a football field, but not larger than the circumference of the Earth. So that's the order of magnitude symbolized here in tan here. So a football field is basically a meter squared or cubed. Then as you get further up, Central Park is a little larger than that. Manhattan would be significantly larger than Central Park. New York State would be larger than that, then the continental United States, and so on. Then as you get really, really high up, you're dealing with massive orders of magnitude that are roughly the size of the universe. And as you get very, very small, you deal with the shortest measurable distance, which is 10 to the negative 20th power, which is difficult to even comprehend because that would be so small. But geographers generally concern themselves with the order of magnitude that are shown here in the tan and the green. So this here is Central Park, a very famous park in New York City. It's about 843 acres, which is actually a little smaller than Belle Isle, which is a park in Detroit in the Detroit River. That's about 900 acres. So Belle Isle is slightly larger than Central Park, but Central Park would be large if you were to compare it to a tree within Central Park, but small if you were to compare it to the city of New York or the state of New York. And then, of course, the city of New York or the state of New York would be small if you were to compare that to the United States here. This is a general purpose map of the US. It shows major landforms. A landform is a major geographic feature related to a specific area. The Appalachian Mountains, the Rocky Mountains, the Great Lakes, and the Atlantic coast would be examples of major landforms in North America. So Unit 2 covers planet Earth. This is Patagonia in South America. That is a llama there. South America didn't have any horses until the Spanish introduced them, so there weren't a lot of pack animals. So people in South America did not ride any animals like they would have in Europe, but they did have some llamas that they might have used to transport goods and so on, but they didn't ride them like they would have in Europe. So here's the largest mountain in South America, Mount A- uh, Aconcagua, and that's 22,852 feet. The largest mountain in North America is Mount McKinley, which is a little shorter, just over 20,000, but they're somewhat similar in size. But that is in Argentina in the Andes Mountains. The Andes Mountains is the longest mountain range in the world and the second tallest after the Himalayas. The Himalayan mountains are far and away the tallest. Mount Everest is over 29,000 feet, which is way higher than anything outside of the Himalayas. So, Earth's geometry and size. This diagram shows how the Earth is slightly larger along the equator than it is at the poles. It's about 40,075 kilometers along the equator and about 40,008 kilometers if you were to measure it from pole to pole. So not a huge difference, but slightly larger at the equator because of the bulge caused by the centrifugal force of the Earth's spinning. And on the right, it kind of shows an exaggerated cross section of that. Again, the poles are a little closer together than the equator would be at its furthest point away. And an ancient geographer named uh, Eratosthenes, it's believed predicted around 200 BC what roughly the size of the Earth's circumference was. And it's believed he did this by looking at a well in Sian, which is a little bit in southern Egypt now, and comparing it to an obelisk or a large tower they had in Alexandria. And he looked at how tall this tower was and how deep the well was. And he looked at them when the sun was directly overhead, so there was no shadow, and you could see all the way down to the bottom of the well, and there was no shadow at the obelisk. And then knowing how tall they were and knowing how far the distance was between them, he's able to use geometry, and hopefully this diagram explains it because I can barely explain it. But he was able to use geometry to predict within about 2% of how large the circumference of the Earth was. So even 200 years BC, there were some geographers, the best in the world, who were able to predict fairly closely what the circumference of the Earth was. But of course, this was a theory. It wasn't really proven until much later. Columbus was aware of the estimate that the Earth was 25,000 miles circumference, but for whatever reason, he thought that it wasn't. He thought that it was 14,000. There were some geographers that thought that it was 14,000, not 25,000. Why he believed that and not the 25 is not entirely clear. But when he sailed across the Atlantic and reached the Bahamas, where it's thought that he first landed, assuming that the Earth was 14,000 feet or miles in circumference, that is roughly where the outskirts of Asia should be. So when he landed in the Bahamas and discovered Cuba and discovered parts of South America, he had 4 trips to the Americas. The Americas were where he thought roughly the outskirts of Asia should be, so it's easy to blame him for thinking, oh, this guy is crazy. How could he not know he discovered a new continent? But based on his inaccurate assumption the Earth was 14,000, not 25,000, the Americas were where he thought Asia should have been. So he had 4 separate voyages to the Americas, and he was a very skilled navigator, but he was wrong in thinking that he was on the outskirts of Asia. Obviously, he wasn't close. So the Earth seems like it's very hilly when you're living on it, but it actually is fairly smooth when you look at the overall size of it. This picture shows an exaggerated version of the Hawaiian Islands. The bumps you see here is vertical dimensions exaggerated by a factor of 50. If you were to look at what the Hawaiian Islands look like without that exaggeration, it would look like this. This is true to scale, and as you can see, when you look at the Earth true to scale, the Hawaiian Islands are barely even visible. The Earth is actually amazingly smooth when you factor in the size of the Earth. So we think of the Earth as being incredibly mountainous, but when you think of how large the Earth is, it's actually relatively smooth overall. So this is an example of Earth's interacting spheres. There is the atmosphere, cryosphere, lithosphere, biosphere, and hydrosphere. The atmosphere, of course, is the air. The cryosphere is all frozen matter, ice, glaciers, and so on. The lithosphere is the Earth's crust, basically the rocky part of the Earth. The biosphere is everything that's living, plants and animals. People would be considered part of the biosphere. And the hydrosphere is considered everything that is water, not frozen like the cryosphere, but lakes, rivers, clouds, and so on. So those are roughly the 5 regional subtypes of geography. The atmosphere goes up roughly 37,000 miles above the Earth. It doesn't exactly stop, it just slowly gets thinner and thinner until it eventually goes out into space. The lithosphere is, again, the outer shell of the Earth that's considered solid. The hydrosphere, oceans are about 71% of the Earth's surface, water is about 72%. And the biosphere is, again, everything that's living, including plants, animals, and dead or decaying organic matter. So a dead plant or a rotting mushroom will be considered part of the biosphere. So this is a picture of basically the Earth, and as I mentioned, about 71% of the Earth is covered in ocean. The Pacific is far and away the largest ocean in the world. It's about a third of the size of the entire planet. The Pacific Ocean is about the size of all land put together. So after the Pacific Ocean, the Atlantic is the second largest, the Indian is slightly smaller, then the Southern Ocean, and then the Arctic. The Southern Ocean is considered basically everything south of 60 degrees latitude south, and it wasn't entirely thought of as its own ocean until fairly recently, but scientists decided the ocean around Antarctica is unique and different enough from the other oceans that it could be classified as its own ocean. So now there are generally considered to be five oceans: Pacific, Atlantic, Indian, the Southern Ocean, and the Arctic. And the Arctic is the northern part of the globe. There's no land mass in the Arctic Ocean. It's all usually snow-covered ice. So if you were to look at the Earth from this particular perspective, this is, if you were to divide the Earth in half, this is the most land you could get in one half of the Earth. And sometimes this is called the land hemisphere. So you can see it has most of Asia, Africa, parts of South America, and almost all of North America. And then the opposite of this would be the water hemisphere. And on the right is if you were to look at the Earth and half of the Earth and you want to maximize the amount of water, minimize the amount of land, the water hemisphere on the right is the most water you could get. So as you can see, there's a lot more water on the Earth than there is land. So the ocean hemisphere is again on the right. It includes Antarctica and Australia, but that's almost mostly including the Pacific Ocean and parts of the Indian Ocean. So you might think that the oceans would get deeper as you get further away from the continents, but that's actually not the case. In the middle of the oceans, there are mid-Atlantic ridges in the Pacific and the Atlantic where the land actually comes up slightly as the different plates are moving away from each other. And the deepest part of the ocean are often in trenches that are sometimes near land. Guam has a series of trenches nearby called Marianas Trench, and it's the deepest part of the ocean. This map here kind of shows the topography of the floor of the ocean. You can see underwater, there are many underwater mountains that are very large, comparable to mountains that we have above ground. So the ocean floor is not perfectly flat by any means. And the deepest part of the ocean is the Marianas Trench, and the deepest part of that trench is called Challenger Deep. And this has been explored on two occasions. A pair of scientists in the 60s actually went down in a submarine to the very bottom of the Marianas Trench. And on the picture here, you can kind of see how deep it is. Military submarines can go a maximum of 900 meters below the water. The Titanic is about 3,800 meters below the water. It's in the Atlantic. You go down even further, at the very bottom, Challenger Deep is about 10,916 meters. So that's about 7,000 feet deep. So that's pretty deep. In addition to the two scientists in the 60s, James Cameron, the guy who directed Avatar and Titanic, wealthy weirdo billionaire, decided that he was going to go down to the bottom of the Marianas Trench. So he used some of his money. The guy's a billionaire. He made Titanic and Avatar after all. And he designed this submarine that actually is relatively simple. Basically, he put it in the water and it just sunk down like a stone. It doesn't have any propellers. And then he went underwater and then he landed at the bottom of the trench after several hours of descending. He took some pictures, did some scientific experiments, and then his submarine released some weights that were in the submarine, and then that made the submarine a lot lighter, and then it started to float up. So it didn't have any machines or propellers. It just sunk. When it was on the bottom, he was done. It dropped the weights that brought him down. Then he started to go right back up like a cork, and it worked. So he did this about 11 years ago on March 27th of 2012, and he went down a total of 7 miles, took a couple pictures, as you can see, took some soil samples. He described the landscape as very lunar. There wasn't a lot there. There weren't a lot of weeds or anything like that. Sort of thought it was fairly desolate looking, and then came back up. So the ocean floor reveals features below the ocean's waters. This is an example of different mid-ocean ridges that are actually significantly higher up than various trenches along the coastal parts of the water. So the mid-ocean ridges are basically parts of the Earth where different plates are moving away from each other. And as they move away, lava comes up from below the Earth's crust, hits the ocean water, and then interacts with it and basically cools. and then that actually creates some certain steam vents. And some of these mid-ocean ridges actually have very odd and unique wildlife that form around where this lava hits the bottom of the ocean. But the ocean gets deeper as you move away from landforms, then starts to get shallower as you move up close to these mid-ocean ridges, and you can see them in the Atlantic, especially also in the Pacific. So here's a cross section of a mid-ocean ridge. You have a continental lithosphere here. You have a subduction zone. That's where land is being pushed underneath another part of land, causing it to get pushed up. South America, the Andes are caused by this subduction zone of a landmass being pushed underneath the South American landmass. And then the mid-ocean ridge, as you can see, is where the lava seeps through the crust, interacts with the ocean, and causes different steam vents. Here's an example of some life along the mid-ocean ridge in the Atlantic. As you can see, they have very odd, unique forms of coral that form along these vents, unusual plants and animals, and so on. So there is quite a bit of life along the mid-ocean ridges where the lava interacts with the ocean here. So this is a distribution of the population in the world. As you can see, the human population on the Earth is not evenly distributed. Certain areas have much larger, denser populations, and they have for centuries. The standouts are India and Eastern China. India and Eastern China, basically, they have a very large population because they have a good climate to support agriculture. They have a climate that has enough rain to support agriculture, but not so much like you might in the tropics that would wash away some of the soil. Too much rain can obviously be bad for farming. So India and Eastern China get a lot of rivers that move through these regions that are fed with snowmelt that accumulates in the Himalayan mountains and then comes down as snowmelt, feeding into the Indus rivers and the Yellow River and other rivers in eastern China and India. So having an environment that can support agriculture is one of the key things that contributes to large populations. You can see the Philippines has a very large population, as does Japan, and so on. Here's another breakdown of population density as of 2020. As you can see here, looks similar to the previous map. Northern India and Eastern China are some of the more densely populated areas. North Central Europe is also very densely populated, has a good soil, and the basically the moderating effect of the Atlantic Gulf Stream helps keep the temperature in Europe cooler than it would be at the same latitude in North America. And then this is kind of interesting. The sphere here contains the majority of people living on Earth. That includes India, Japan, China, parts of Indonesia. There are more people living inside of that circle than outside, which just goes to show you how densely populated many parts of Asia are, especially India, China, and Japan. At the moment, the largest city on Earth is Tokyo, Japan. It has a metropolitan area of about 37.8 million. And of course, it's kind of hard to judge how big a city is. First of all, you have to be able to conduct an accurate census, and it's very difficult to count 37 million people. And also, you have to decide where exactly does the city end. Is it the city proper? Is it everything within a commutable distance of the downtown? Is it, what if a city bumps up into another city? So where you decide a city ends kind of determines how large that city is. But by most accounts, Tokyo is the largest city on Earth. Previously, it was New York. Tokyo surpassed New York in about the 1960s. And in the near future, it's possible that New Delhi, India, or Shanghai might surpass Tokyo. It's unlikely Shanghai will because China's population is actually starting to level off or even decline. But New Delhi is in India, and India's population is still growing fairly quickly. So one of these two cities, especially possibly New Delhi or a city in India, may surpass Tokyo in the near future for the largest city on Earth. India is likely to surpass China as the largest country on Earth within the next 4 to 6 years. So Unit 3 is mapping the Earth's surface. This is the Royal Observatory in Greenwich, London. This is basically where the prime meridian is, the line that separates the Western Hemisphere from the Eastern Hemisphere. It's sort of arbitrary where this was, but when it was selected in the 1880s, Great Britain was a major global empire. So it made as much sense to put it somewhere in England as anywhere. And this observatory contributed significantly to the study of geography and astronomy. So it was thought, well, why don't we put it kind of right in this observatory on the outskirts of London and make that the separation between the eastern and western hemisphere. And by putting it there, it also made the opposite end, the international date line, go through a relatively lightly populated part of the Pacific, because it can be kind of confusing if the international date line went through a heavily populated part of the world. So this is where the line of longitude starts, basically on the outskirts of London at this observatory. So the Earth is uh, this system of categorizing the Earth in northern and southern hemispheres and longitude and latitude and so on was kind of created by people for the purpose of making sense of the Earth and navigation. Lines of latitude are lines that are parallel to each other, and they measure north-south, but they run east-west. They can be a little confusing, but they go from the east to the west, but they measure north-south. They're like rungs of a ladder. They're parallel to each other. When you think of latitude, try to imagine a ladder and rungs on a ladder. And then lines of longitude run north to south, but measure east-west. They are wider at the equator, then they converge at the poles of the northern and southern hemisphere. And these two systems together make up a geographic grid that we experimented with in our first lab that categorizes things into the northern and southern hemisphere, or eastern or western hemisphere. Northern hemisphere positive, eastern hemisphere is positive. So something in the western part of the hemisphere, in the southern part, like Buenos Aires, would be negative, negative as far as degrees of latitude and longitude go. So we're used to maps having north at the top, but that wasn't always the case. Historically, east and south were usually the easiest positions to determine, because if you're in the northern hemisphere, the sun at the highest point of the day will always be to the south of you, and east is where the sun always rises. So usually in ancient times and medieval times, east was placed at the top of the map. There's no reason why it has to be east or north or anything. And then starting in about the 1500s, it was switched and north became the top. But on the left is a map of Rome with east towards the top. And on the right is what's called a T map. And this was a very simplified map common in the Middle Ages that put Jerusalem in the center, Europe on the bottom left, Africa on the bottom right, Asia on the top, which was to the east of Europe, and then the Red Sea, or the Nile, was sort of the dividing line between the east and the west, and then the Mediterranean Sea separated Europe from Africa. So this is what a typical map in the Middle Ages would have looked like. It's a very simple map called a T map. So lines of latitude and longitude. The equator, of course, would be considered zero, and then if you were to kind of move upward 30 degrees north, as you can see is illustrated on the top here, 60 degrees north is about two-thirds of the distance between the equator and the North Pole, and then 90 degrees would be the North Pole. So the top map shows kind of a cross-section of latitude starting at 0, going up to 90. The Tropic of Cancer is at 23.5 degrees latitude north, and the Tropic of Capricorn is 23.5 degrees latitude south. And if you are within the tropics, that means at any given time in the year, the sun will be directly overhead. Those are the parts of the earth that get the most direct sunlight. The second map on the bottom here shows longitude. This imagines you're looking at the earth from the top down, looking at the North Pole. It shows New York longitude about 42 degrees latitude north, I believe. Tokyo is a little bit further south. And then you can kind of see that if you were to fly in a straight line from New York to Tokyo, you'd sort of fly almost over the North Pole. And then on the bottom, it shows, again, lines of latitude and longitude of New York City compared to the prime meridian and compared to the equator. So New York is 40 degrees north, roughly, and 73 degrees to the west. And a little bit about these lines of latitude and longitude. People would often use degrees, minutes, and seconds. A degree would be, there are again 90 degrees from the poles to the North Pole. Then those would be broken down into minutes, which would be further broken down into seconds. Now most people use decimal degrees. It's just a lot easier. So instead of saying 72, 1755, you just say 72.29, 72.41. So it's just B is what's more commonly used, where you just say the decimal degrees as opposed to trying to break it down into minutes and seconds and so on. So if you were to fly from New York to Tokyo, interestingly enough, one of the busiest cargo airports in the world is in Anchorage, Alaska. And the reason is it's almost exactly halfway between New York and Tokyo if you were to fly in the direct route. And planes can stop and refuel in anchorage, and because they can, it means they don't have to carry as much fuel, which means they can carry more cargo, which is more profitable. So even though you could fly from New York to Tokyo with enough fuel, they deliberately carry less fuel so they can carry more cargo. Cargo ships land in Anchorage, they refuel, then they fly the second leg to Tokyo or Beijing or Seoul or so Anchorage, Alaska, even though it seems remote, is one of the busiest cargo airports in the world. So a big part of geography now are global positioning systems. These are basically a series of satellites in the sky and in space that can help triangulate a position on Earth with great precision. They were developed in the 50s and 60s. It was developed by the U.S. military and mostly in the 1970s, became fully operational in the mid 90s. The military would deliberately scramble the accuracy of global positioning systems for security reasons, but in 2000 they removed this deliberate scrambling of the accuracy of GPS systems, and then they became more common to use in everyday items like your cell phone, geocaching. That's kind of a hobby where people will hide something and then post the latitude and longitude on a website, and then you kind of go find it. And it's used in navigation and used by the military and so on. So now it has many different purposes. It can work in remote areas. You just have to have at least three satellites that can triangulate your position. And then based on that, you can, with a great degree of accuracy, often within less than a meter, find your location anywhere on the Earth. Here's a quick diagram of how it works. You don't have to memorize this, but essentially, three satellites track your location. You send out a signal, then they see how long it takes to send the signal out, then get the signal back. Then they can use that to determine how far away you are. And if you have three satellites, then they can, with a high degree of actually triangulate your position on Earth. And now it's used in navigation and so many other things. So when you take something like the Earth, which is round, and try to make it flat, inevitably there are going to be some distortions. And to try to deal with this, different geographers and cartographers have created different map projections that try to minimize distortion or try to emphasize what's most important for whatever map you're trying to use. So here we have some examples of a cylindrical style of map projection where you kind of imagine the Earth as sort of a cylinder and then you flatten it. The Mercator projection is a type of that. Then you have conic map projections, which imagines that one half of the Earth is a cone, and then you kind of flatten it out to see what it would look like that way. So a projection, this is kind of a visual example of what it would be like. You imagine that there's the Earth, and then you have lines of latitude and longitude, and then you have a light inside of it. The projection is how you would take that grid and then kind of flatten it onto a flat surface. So this is sort of a visual representation of what a projection would be if you were looking at perhaps the northern or southern parts of the globe. So one of the most famous projections is the Mercator projection. Mercator was a Flemish geographer who lived in the 1500s. He lived to be 82 years old, so he actually lived a long time, got to do a lot of research. But he wanted a map that would be used for sailors, mostly sailing in the northern hemisphere, and it was important for him to keep the proper shape of different land masses. So his map, using the Mercator projection, which is still used in Google Earth, kind of distorted the size of land masses in the northern and southern hemispheres, but was able to correctly preserve the shapes of them. It was also used for navigation because using this kind of map, you could sail from one place to another on one consistent compass bearing without having to constantly recalculate. So if you wanted to sail from London to New York using the Mercator projection, you could just sail, figure out what bearing you needed to go on, and continuously go along that bearing on a compass, and then get to New York. It wasn't the quickest way. The quickest way would be if you were to sail along a great circle, which is basically any line that divides a sphere into two even parts. The line where you're going on one consistent compass bearing is called a Rube line, but in navigation before GPS, Rube lines were very commonly used. So it distorted the size of land masses in the northern and southern hemisphere, but was very good if you were wanting to navigate over the ocean in as simple and straightforward a way as possible. So equal area projections try to preserve the relative size of things. One way to preserve the shape and size of maps is to kind of break up the maps into smaller parts. That style of map is called an interrupted map, or you kind of will often break up the ocean into different parts so you can preserve the proper shape and size of different land masses. So that's one way to do it, but really there's no perfect map. You're always going to have some distortions of some kind. One of the most common projections now is the Robinson projection. National Geographic used this for, I think, up until 1998. And this is kind of a compromise where you have roughly the same size and shape as most land masses are, but even this exaggerates the size of land masses in the northern and southern parts of the planet and minimizes the size of Africa, South America, and elsewhere. In real life, Greenland's about the size of Mexico, but in most maps it looks a lot larger because of distortion. And Antarctica is slightly larger than Australia, while it looks significantly larger in this map. Another map commonly used now is called the Winkel-Tripel projection. I think National Geo adopted this in 1998 as their default map projection. And again, this corrects somewhat the size. It more accurately shows the size of South America and Africa. But this map, you can see the poles bend away towards the edge of the map, while in real life, lines of latitude are parallel to each other. So even this map has some distortions and flaws. So another kind of map that's fairly common is an isoline or isometric map. These maps are maps that are often used to show rainfall or temperatures. And in this style of map, you basically have lines or color codings that represent a certain amount of sunlight or a certain amount of temperature or a certain amount of rain. This particular map is showing the average annual rainfall from 1956 to 1980 in Florida. And as you can see, blue areas represent more rainfall, lighter areas represent less rainfall, and the lines are kind of the dividing line between different amounts of rainfall. So that style of map is called an isometric or isoline map. They're also commonly used when you're talking about temperatures. This is an isometric map of the United States showing what temperatures are like in the summer and in the winter. And as you can see here, the redder it is, the warmer it is, and then the lighter the color, the darker, the colder it is. Another kind of isometric map is used to show height or elevation or topography. This is a topographic contour map. These are fairly common. And the top map shows a hill if you were to look down on it from the top. These little circles represent an elevation above the sea level. So 520 is 520 feet above sea level, 510, 500, and so on. The closer the lines are to each other on this map, it means the more dramatic the change in altitude is. Lines that are real bunched together means a very sharp slope or decline. Lines that are further apart means a more gradual change in elevation. So this is, again, a map. If you look at the bottom, that's a cross section of the map you see on the top. So 500 meters above sea level here is 500 meters above sea level there. So this X and Y is kind of a cross section represented on the bottom of this map here. So this is a similar map shown kind of with a 3D view on the top. This is also a coastline, I think, along the Pacific, and it shows significant change in elevation where the lines are bunched close together, which is represented, as you can see on the map at the top, that shows a sharp cliff. And then where they're further apart, it's a more gradual ascent in elevation. So one thing that I work with at my job is geographic information systems. I'm the GIS coordinator for the city of Jackson. And GIS stands for Geographic Information Systems, and it's a series of computer software programs that collect and analyze data that can be used for many different purposes. The example they give here is you have one computer layer of bedrock, one with soil types, one with vegetation types, and then on the bottom, physical or geographic composition, and then you can stack those layers on top of each other. One thing that I do is I deal a lot with storm sewer lines, water lines, zoning maps, parcels, and a lot of other maps like that. So I'll often have a map that will have parcel lines placed over zoning, or water service lines or water sewer lines placed over streets and so on. And it's used a lot for asset management, for keeping track of different infrastructure within the in the city. So remote sensing is sort of a branch of geographic information systems. Essentially, it's anything where you collect information from a distance. Satellites would be an example of remote sensing. Aircraft that are taking aerial photos of something would be an example of remote sensing. You could have ground-based radar or infrared remote sensing. This particular picture is a Landsat image of the Los Angeles area. In this particular picture, red is vegetation, and urban areas are represented in blue and gray, and then water is black. And as you can see here, the built-up urban areas have a lot more bluish gray, and then the wilderness areas, the mountainous areas without as much cities or streets are portrayed in red, and then the ocean is in black. And like we talked about earlier, areas where you have a lot of built up urbanization, cities, not a lot of vegetation, you also have warmer temperatures. On the left, this is a percentage of tree cover in the Los Angeles area. And on the right is surface temperature. As you can see very clearly, where you have very few trees, because you have roads and highways, you have a lot hotter temperatures. Mountainous areas that are woods and so on can be 60 degrees. And on the same day, along a major street, it can be 90 degrees. So you can have a variation of 30 degrees based on how much vegetation and shade an area has. So remote sensing of the environment. Um, what we see when we see with our eyes is the visible light spectrum, and that's only a very small band of the wavelengths that are given off by stars and light and so on. So where you have shortwave energy, where you have things that you can't see with a visible eye, you can see. We see this again, this visible light spectrum. But if you get wavelengths that are shorter, then you have ultraviolet, then you have X-rays, then you have waves that are really, really close together, are cosmic rays or gamma rays. And then at the other end, when wavelengths become further and further apart, when a wavelength is much longer, you have infrared, microwave, radio spectrums, and so on. What we deal with, what we see is the visible light spectrum, which is only a relatively small part of the wavelengths of energy emitted from stars. So what we see is only a small amount of the energy that's out there emitted from stars in our sun. So Sun-Earth relations. The Earth, of course, revolves around the sun, and a rotation is roughly 24 hours. A revolution is roughly 365 days. The Earth has a 23.5-degree tilt, and that tilt is what creates our seasons. If the Earth had no tilt, we would have no seasons or very little variation in seasons because the amount of sun and the intensity of the sun hitting where we live on Earth would be relatively unchanged. So time zones were invented by people after railroads were invented. We'll talk about that in a little bit. So the point where the Earth is closest to the sun is actually during the northern hemisphere's winter on January 3rd. It seems counterintuitive that if we're closer to the sun, it should be warmer, but the distance really isn't that much. You're about 1% closer on January 3rd than you would be at the furthest point away on July 4th. We're roughly 93 million miles on average, about 92 million miles on January 3rd, and roughly 94 million miles away on July 4th. So that isn't enough to feel any difference. What determines the temperature is the amount and the directness of the sun's light hitting the earth of where you are. So the more the sun's rays hit you, the more directly you are hit by the sun's rays, the warmer it is. So this is an example of the earth revolving around the sun. Again, it's 147 kilometers roughly. The earth revolves around the sun in an elliptical path, although it's close to a circle, it's slightly elliptical. And a revolution is 364.25 days. That's why we have leap years to correct for that. The Earth's usually about 93 million miles away, but at the closest it's 91.5 million, and at the furthest away it's 94.5 million. And this is a diagram kind of showing the 23-degree tilt of the Earth. Talking about the annual cycle is how long it takes the Earth to revolve around the sun, and then the rotation being how long days and nights would be here. Declination of the Earth's axis, that is basically the tilt of the Earth. Again, we're 23.5 degrees. Mars is actually 25-degree tilt, so just a little bit more than Earth. Venus is actually almost upside down. It's almost straight up, but because it rotates the opposite direction of the Earth, scientists consider it to be upside down, and it has about a 175-degree tilt. And then Uranus is almost sideways. It has about a 90-degree tilt. So different planets, even within one solar system, can have significantly different degrees of tilt. And ours is about 23.5. So what this means is if you are in the northern hemisphere and it's June, you're above the Arctic Circle. That means that the sun will be above the horizon for several days. And if you're at the North Pole, it can be several weeks. So this is an example looking towards the North Pole on August 1st in a city in Alaska. And this is a time-lapsed picture, but it kind of shows the sun hovering near the horizon but never dropping below it. So if you're on the very northern part of the Earth or southern part above the Arctic or Antarctic Circle or below the Antarctic Circle, that means for a certain time of the year, the sun will never set. It will hover just around the horizon but not completely set. Way up north, there's a seed vault that's kind of interesting that was built in Norway. And the idea is Norway has quite a bit of oil money. They wanted to do something useful for the world with their oil money. So they spent their own money to create a seed vault. And now they collect seeds from all over the world that are endangered. So if a certain seed for a certain type of rice or wheat goes extinct, they have a copy of that seed that can be withdrawn from their library of seeds, and they keep it way, way north of the Arctic Circle because it's very cold, and the cold weather helps preserve the seeds. So this is a bunker buried way above the Arctic Circle on an island that's part of Norway, and they have thousands and thousands of seeds, 5,972 different kinds of seeds in the seed vault. So I thought that's kind of interesting. So this is a picture of a person if they were hypothetically to stand on the equator. You can see if it was June 22nd and you were standing on the equator, the sun would be 23 and a half degrees to the north of you. And if you were to stand on the equator on December 22nd, the sun would be 22 and a half degrees and 23 and a half degrees to the south of you. So this kind of puts into real world terms what it means like to have the tilt of the earth if you were to be on the equator. This diagram kind of shows where the Earth is at different times of year in the seasons that we would have. So on the top, it's pretty close to where we are now. The equinox, March 21st, usually the vernal equinox means that you have even amount of daylight and darkness basically all over the Earth. And you have basically roughly 12 hours of daylight, 12 hours of darkness. And then as you continue along this orbit, you have more sunlight during the summer in the northern hemisphere, less sunlight in the southern hemisphere that time of year, and so on. So time zones are kind of interesting. Um, Before time zones were invented, they were invented in the late 1800s. Most towns had their own unique time zone. A town would have a sundial, and then they would set their clocks to whatever the sundial was. So when the sun was at the highest point of the day, that was their noon. And when the fastest you could travel was generally as fast as you could walk or ride a horse, that worked out very well. But then when trains started to become common in the late 1800s, you had trains that would go at much longer distances at much faster speeds, and then it became very confusing having all these changing time zones between one city and another. So the prime meridian, as we mentioned, was decided that it would be in London in the late 1800s, and then these lines were created that have different time zones. In the US, we have four different time zones. India is all on one time zone, and China is also all on one time zone. They just thought it would be easier for their country to be on one time zone. Most countries divide them up roughly along lines of longitude as we have here, and we have four major time zones. But basically, these are an artificial creation created by people, and that's why the lines aren't particularly straight. They're drawn to be convenient to certain areas. The Eastern time zone goes basically to all of Michigan except a tiny part of the UP. And then a small part of Gary, Indiana is actually in the Central time zone. That's because it's a suburb of Chicago. So they thought it'd be easier if people who might commute to Chicago were in the Central time zone. So most of Indiana is in the same time zone as Michigan, but a small part of Gary, Indiana is in the Central time zone. So this is a diagram of the intensity of sunlight. As you can see here, where the sun hits the earth more directly, there is greater temperature on average. The equator gets the most direct sunlight from the sun. And then as you get towards the poles, the sun's rays hit that part of the earth at more of an angle and it's more of a glancing blow. So it's not as warm. So unit 5, radiation and the heat balance on Earth. This is an interesting picture. This is the Grand Canyon, and this is a picture of Douglas firs. And generally, Douglas firs can't survive in the Grand Canyon because it's too hot. But some of them that grow on the northern side of a slope, like pictured here, can grow because they're more shaded. Being on the side of a hill that faces north means that the shadow of the hill makes it a little bit cooler. So there are certain parts of the Grand Canyon where you can have Douglas firs if they're on the northern side of a slope. So this talks about solar and terrestrial radiation. Basically, radiation is light and heat from the sun, and it basically kind of shows the different wavelengths of short wave and long wave radiation. So on, you can kind of look at this in the book. And it talks about heat transfer. Conduction is when you have heat that moves through a solid object, molecule to molecule. So if you had a frying pan and you put it on a fire and you held the frying pan without a heat guard or something, the heat would travel through the frying pan into the handle and it could get hot. That is an example of conduction, basically heat moving through solid objects. Convection is heat that's transferred by movement, usually heat transferred by water or by air. So if you were in the water and then you had a warm wave or a cold wave that hit you, that would be an example of convection, or a cold front or cold air blowing in will be convection. So conduction is heat traveling within a substance, and convection is air or water current and heat traveling from one place to another by fluid motion. So the soil gets significantly warmer during the summer and the day compared to the night. Basically, there's not as much of a change in soil temperature from the day to the night compared to the summer to the winter. But during the day, the top does get a little warmer, and then during the nighttime, the warmth kind of moves from the lower parts of the soil up towards the night, and then that cools the dirt. And then, as you can see on the right here, a similar pattern happens during the summer and the winter. During the summer, the top of the soil is warmer, the bottom of the soil is colder by comparison. During the winter, that kind of shifts. You get further below the top of the surface, and it's actually warmer than the soil that's closer to the surface, that's in contact with the snow and so on. So these are different temperature cycles and temperature changes in soil between daytime and the change of the seasons. So latent and sensible heat transfer. Um, Basically, latent and sensible heat transfer. A sensible heat transfer is movement of temperature, of heat, of energy, and latent heat transfer is usually refers to moisture. So the diagram here talks about how warmer air temperatures are heated up on the Earth's surface, then it moves up into the atmosphere where it's cooled, and that creates some mixing. And on the right, latent heat transfer talks about how sunlight might hit a lake, that causes evaporation, and then the moisture moves up into the air, increasing the moisture of the air, and that would be an example of latent heat transfer. So essentially, sensible heat transfer is temperature, and latent heat transfer is evaporation and moisture. So the radiation balance on Earth, we get a lot of incoming radiation or energy from the sun. About 32% of the energy we get from the sun actually hits the Earth's surface. A large amount of it is absorbed by dust and molecules in the air, or scattered back into space, or reflected by clouds back into space, or it bounces off of clouds and then indirectly hits the Earth after hitting clouds. So this kind of shows a diagram of what happens to the energy from the sun as it hits the Earth. About a third of it directly hits the Earth, and about 22% bounces off clouds and then directly hits the Earth. And then about 7% is reflected off of the Earth in the form of radiation. So this is an example of the albedo effect. Basically, that is when you have a surface that is very shiny or snow, and it reflects a lot more of the sun's rays than a darker surface that would absorb more. So fresh snow has an 80 to 95% albedo rate. That means it reflects about 80 to 95% of the sun's rays, while blacktop or asphalt has only about a 5 or 10% albedo rate. So solar panels are black because the darker it is, the more of the sun's rays it absorbs. And if you want to keep a building cool, you'll often paint it white because then it will reflect more of the sun's rays. So as you can see here, the moon reflects about 6 to 8% of the sun's rays. And there can be a big variation in the albedo effect of different surfaces of the Earth. A scientist at Purdue created what is considered to be the whitest paint on Earth. He is a professor of mechanical engineering named Zuling Wan. And this paint that he created about 2 years ago reflects 95.5% of the light that hits it. So that means it reflects so much, You might not even need to have air conditioning if a building was covered in this kind of paint. So scientists are hoping that if enough buildings could be painted in this specific kind of paint or just any white paint in general, it might eliminate or reduce the need for air conditioning, which is a very energy intensive industry. Air conditioning uses a lot of electricity, sometimes coming from fossil fuels, which only exacerbate the problem of global warming. So here's an example of a building that's painted white. The top right shows a picture of bricks that are painted white. It's very common for buildings to maybe paint the roofs white if they are in a hot environment to try to reflect heat and then keep the building cooler. So this is an example of basically having energy from the sun absorb into the Earth's atmosphere. The Earth and the atmosphere actually absorb a significant amount of the energy from the sun, and the atmosphere actually emits about 1.5 times the amount of incoming solar radiation. So that means that the Earth and the atmosphere absorb and emit slightly more energy than the amount of energy that hits the Earth. So this is kind of a breakdown of what happens to energy hitting the Earth. Some of it is some of it is released as sensible heat, some of it is released as latent heat in the form of convection, and some of it's absorbed in the atmosphere, and a small portion of it is reflected back into space. But essentially, most of the heat we have from the Earth is heat that's been absorbed by the Earth and the atmosphere, and then later released, not necessarily heat coming directly from the sun. So where does the heat go? This is an example of what happens to most of the heat that hits the Earth. The vast majority of energy and heat that hits the Earth is absorbed into our oceans. About 84% is absorbed in the oceans. The atmosphere is about 4%. The continents and land masses is about 5%. And then ice is about 7%, which is higher than it might seem, but still fairly large. So far and away, the ocean absorbs most of the Earth's heat. It heats more slowly than land and cools more slowly than land. This is a global distribution of the heat based on latitude. And as you can see on the top, there's a lot more incoming solar radiation hitting in the equator and the equatorial regions. And then as you get further towards the poles, there's a lot less heat. So what that means is there's an imbalance where there's more energy along the equator and less energy towards the poles, and that causes heat to move from the equator towards the poles, as we talked about earlier with our example in Siberia. So this causes a lot of the movement in the atmosphere where moisture and heat, especially heat from the equatorial regions, is pulled towards the colder regions, towards the poles in the northern and southern hemisphere. And as you can see on the bottom, a similar situation happens with the oceans, but at a smaller scale because the oceans heat and cool more slowly. So that is it for part one, the first 5 units. Hopefully, it wasn't too boring. The next one we have will cover more units, but I try to keep this presentation at roughly an hour so it doesn't get too tedious. So if anyone has any questions, I'll be happy to answer it. If you have a microphone or if you want to send me a text, I'll minimize my presentation here so I can see any incoming texts. Otherwise, if there are no questions, thank you for joining me. You can send me an email if you think of something a little later, and have a good evening.